So welcome to this ARDC, Australian Biocommons webinar. Through these sessions, we hope to share useful information about the latest digital techniques, data and tools. My name's Christina Hall and I'm the Australian Biocommons Training and Communications Manager, and we have Susanna Bacon from ARDC behind the scenes making today's session work. Before we start today, I'd like to acknowledge the traditional owners of the lands on which we work and pay our respects to the elders past, present and emerging. We really appreciate those of you joining us live today, and you'll have the opportunity to ask our speaker questions directly via the Q&A function on your dashboard, and these will be addressed at the end of the presentation. This session will also be recorded, and if you'd like to revisit it in the future, you'll find it on the Australian Biocommons and ARDC YouTube channels, along with recordings of previous webinars and workshops. We also hope you'll keep in touch to hear about future webinars via the channels listed on the screen here. Today, we're thrilled to welcome Jason Coposky, who is the Executive Director of the iRODS Consortium. Jason joins us today from North Carolina, well and truly outside of his normal business hours. Unfortunately, he didn't travel to Melbourne as planned due to COVID-19 conference cancellations and travel disruptions, so we really appreciate his willingness to join us from home. Jason comes to us today with a wealth of industry experience, having worked in a variety of areas, including virtual reality, electronic design, automation, visualization, and data management. Now working at the Renaissance Computing Institute at the University of North Carolina at Chapel Hill, Jason has moved from technical lead of the iRODS project to chief technologist and now executive director of the iRODS Consortium. In his presentation today, Jason will tell us about the open source data management software, iRODS.
All right, thank you. Can we see the slides? So to start, we'll discuss the organization a little bit. So the iRODS Consortium is a sustainability model that has been wrapped around a project with 20 years of history. The idea here is this consortium supports and sustains the development as well as the community that is currently using iRODS. iRODS, as we heard, is housed at the Renaissance Computing Institute, which is an applied research organization at UNC Chapel Hill, and we effectively do business as the University of North Carolina. Our membership includes anything from research institutes to commercial storage vendors to enterprise users like Bayer and so on. We have about 25 to 30 members at this point, each of which pay a yearly fee to the consortium to help sustain the consortium development of the iRODS software, as well as to help us provide support to the community. Speaking to the technology, iRODS is a distributed system. It runs on a laptop. It runs on a HPC cluster. It can run on a Raspberry Pi. It can run all locally or geographically distributed, as well as on-premises and within a multi-cloud environment. It has BSD3 license. We provide a package repository. It's free to install and free to use, which is why we use a consortium model in order to sustain and support this software. And the two key takeaways here is that iRODS is metadata driven and data centric. Everything that this software does with metadata or with data revolves around metadata. And our idea here is that we insulate both the data and the users from the infrastructure, which we assume is going to grow and shift and change, as well as the future use cases for your data management. So I like to describe iRODS as a layer that sits above all of the existing infrastructure and provides the ability to integrate horizontally across all of the different infrastructure within your data center, on premises or off, which includes storage, but this also includes compute. So how does your data interact with your analytics platforms, possibly indexing for future discovery, as well as authentication and authorization infrastructure. iRODS provides that insulation layer above all of that infrastructure and provides a consistent use or experience to your users, whether it be on the command line, it could be a web dev folder on your desktop, it could be a rich discovery environment such as a web application and so on. And the way that we achieve this, starting at the bottom of the technology stack, is with our 4 core competencies, which are effectively just names that we have provided to bundles of features within the software so we can provide some way of talking about this. The first of which is data virtualization. So data virtualization speaks to iRODS' ability to sit above all of those different kinds of disparate storage systems through our plugin interface and gives us the ability to project all of that underlying storage into a unified namespace. So this could be on-premises filers, this could be on-prem object storage, off-prem object storage in a cloud or in the multi-cloud, as well as archival storage systems. And through our plugin interface, this provides a future-proof to all of your existing storage. So we can consider this at the bottom of the layer here, the infrastructure layer, where we have a number of servers. All of these servers are surfacing some sort of storage technology into iRODS and into this virtual file system, or what we like to call the unified namespace. Within this unified namespace, data is organized logically within collections that exist only within the catalog. And as we drill down to the specific data objects, those data objects are logically represented within the catalog and may represent one or more physical instantiations of the data or replicas that can exist on any storage technology. It is up to this virtualization layer to make decisions about which particular replica users might interact and how those replicas may be moved around the different storage systems themselves. Since iRODS is effectively a catalog and a network protocol, we have the ability to attach metadata to any entity within the system as well. So we can attach metadata to data objects in order to make those actionable and discoverable, collections of data, of course, for the same reasons, but we also have the ability to attach metadata to users, the storage resources, and the namespace itself. And this is what makes all of these entities within the system actionable. And the way that we take action is through an integrated scripting engine. So if we take a look at a simple example here, we have users, let's say a physician, Alice, who has metadata attached to her that identifies her as a scientist or a physician. We can have metadata attached to the data objects in the collections in order to make those discoverable by the users through queries, but we can also attach metadata to these storage servers down here, which also give them an identity. So we can indicate that, say, the green server down here has storage attached to a GPU cluster. We can indicate that the blue server here has storage which might be HIPAA or GDPR compliant. And we can indicate that the orange server has storage out, let's say, in the cloud in Amazon. As the scientist shows up with data and wishes to put it within the unified namespace, the system itself can make decisions about that data. What kind of data is it? Who is the user that is providing this data? And where should we route this data? So since Alice has indicated that she happens to be a physician, that data may be routed to the blue server because it has personally identifiable health information. But if Alice shows up with a .com file from an MRI system scanner, for instance, we may route that to the GPU cluster because we know that that data is going to be positioned for further analytics, specifically using those GPUs. And if it is not a physician, let's say an intern shows up, we can route that data directly out to the cloud and leave it there until we need it. And the way that we go about this is through this integrated scripting engine, which is in a language of your choice, which gives us the ability to take this action. Every plugin interface from authentication all the way out to the extensible RPC API has policy enforcement points associated with them based on the architecture of the system. And this is where we can take real-world data management policy and then reflect that in computer actionable code. So to further investigate our example here, we have Alice, our physician, who shows up and invokes the put API, which has a pre-policy enforcement point or a hook where you can implement your particular code for your data management policy. In our previous example, we would examine the metadata associated with Alice. We can examine the file type that Alice wants to put into the system. And then we can make some decisions about how that data should be routed. Should it go to the green box, the blue box, or the orange box? Assuming this pre-hook is successful, the data will flow into the system, the RPC API event will actually fire, and then a post hook will be invoked, which is where we like to do things like send a message that the data has been uploaded, or perhaps extract metadata automatically out of that data object. Say if it was the .com file, we can pull the open microscopy XML out of that data object and put that into the catalog to make it immediately discoverable. We could send a notice to a log stating that this event has happened and who has performed that for an audit trail. Or if the intern shows up and tries to directly put data specifically into the blue box that has the compliance wrapped around it, then we can immediately restrict access. If the pre-hook fails, then the operation does not perform, and then we have an accept operation here, or accept policy enforcement point, that would then also be fired in order to capture the negative space around what was disallowed. Now for this example, a single RPC API has a pre and post hook, But the single RPC API call fans out to about 1,200 different operations within the system that may also have policy associated with them. This is where the future-proofness of the system comes into play, wherein we can abstract the infrastructure in order to provide the ability to move horizontally within the system. Let's say you decide to decommission a particular storage system. You can simply replicate that data to a new storage system under the covers, mark it read-only, and then eventually decommission it. Using this particular policy layer, we have the ability to think into the future for your future requirements around your data management policy itself. We can't decide what is going to happen to data 10 years down the road, so we have to have the ability to be as flexible as possible with our data management. The last of our 4 core competencies is what we call secure collaboration, which speaks to the ability of iRODS to federate catalogs. iRODS is a distributed system. Servers can talk to servers. There's no reason why a server in one namespace can't talk to a server in another namespace. We simply generate a set of keys that represent that relationship, provide them configuration, and then immediately start collaborating. All we simply have to do is create users in either zone that is going to have access to the shared data, and then you can build virtual collections of data across time and space and institutional boundaries. There is no need for common funding or common infrastructure, and this very much affords temporary collaborations. If this federation is no longer needed because the project has ended, you can simply delete the keys and remove the users, and you are right back where you started. So if we think back to, say, the second slide where iRODS was sitting above all of that infrastructure and wrap it around that infrastructure, we effectively create a service layer or a policy layer around that infrastructure. And taken into the context of federation, while we are building virtual collections of data across institutional boundaries, we are beholden to the data management policy in our collaborators' unified namespace or zone. When we're interacting with data in our collaborators' namespace, we are going to be restricted by their policy. If that data happens to be residing on a blue box, for instance, that has compliance wrapped around it, and we're not allowed to copy that data into our zone, we can, using this service layer, have the ability to reach out and containerize our applications and run that application where the data is at rest in order to gather those results. Now, whether those results are also allowed to exfiltrate that particular zone is a different story, but the key takeaway here is that we have the ability to reach into much more of the infrastructure due to that horizontal integration than just necessarily the data that is presented through the unified namespace. And ultimately, it comes down to the data lifecycle. As data matures, that data management policy is going to change and shift and grow as the data moves through the life cycle. When data is immediately ingested, it's very simple. That is my data. Users are not allowed to touch it. But of course, we're going to do something with that data, perform some analytics on that data. Discoveries may be made, and then we may want to collaborate with the user. So we're going to share that data. That user may be in another zone. It may be in another institute. Regardless, it doesn't really matter because that data management policy has now shifted from private data to semi-private data. If discoveries are made, papers are published, the data must be published along with those papers. We want to issue a persistent identifier like a DOI or a handle, and then publish that data to some sort of external catalog, or at least provide a reference to it through the internet through a RESTful interface. Now that data must become immutable because it is a snapshot in time, and that is a completely separate data management policy. Perhaps it becomes part of a reference collection, or it needs to be preserved into the future, and so on and so forth. So the idea here is that as that data matures, the system that is managing that data must mature along with it in order to provide those shifting data management policies throughout the lifecycle. So moving up the stack of the technology, we've talked about the underlying core competencies, basically as close to the server as possible. Above that server, we've spoken a lot about policy, that reflection of that real world data management decisions, or what we call a plan of what to do in a particular situation. And these plans are effectively made by people sitting around a table coming to decisions. Once those decisions are made, the interesting part about this system is that you can now automate those decisions and enforce those decisions automatically. So how do we do this? Effectively, as I said, we take a reflection of that policy and implement that in code. Now, this is not necessarily a project wherein you are responsible for implementing every last one of those policies yourself. As a consortium, we survey the community, if you will, and then from there decide what parts of these policies that we can provide off the shelf in order for you to configure those. So this may be ingesting data, this may be moving data horizontally or vertically through the storage systems. This may be verifying that data is correct at rest. This may be a decision around when you are allowed to delete the data, where that data must be routed, as we've discussed earlier, and so on and so forth. All of these are simple policies, or the what, that you want to actually enforce in order to provide that reflection of your data management policy within the configuration of the iRODS system itself. So from there, we can take these policies and implement these policies together in what we call capabilities. They're not necessarily Legos, but as close as we can possibly provide, where we can configure any number of these data management policies in order to achieve a particular outcome. These policies are invoked through these dynamic policy enforcement points that I had mentioned earlier, and they can be configured in any number of ways. So speaking to the what being the policy itself, the when is going to be these policy enforcement points. And we can take a simple look at the RPC API here. I mean, this is any number of operations when the system can basically be boiled down into a series of events. Data creation, someone is writing to an existing data object, someone is reading a data object, someone's going to remove that data object, and so on. And those events will then drive the data management policy. So we can consider in an existing example what we call storage tiering. The automatic movement of data through the system is effectively composed of a number of existing policies. So this could be the identification of a data object that is violating its policy and then must be moved. This could be the data movement policy itself, which is effectively data replication, and then the verification of that data at rest. And then ultimately data retention. Do we retain the previous replica of that data, or should we trim it away? And the one true authoritative replica will be at the next tier within the storage tiering. So as a consortium, we have identified about 8 different capabilities that most of our users want out of the box. As I've spoken to storage tiering, we also will investigate automated ingest. How can we automate the ingest of data at the edge and bring the data management policy as close to that data origination as possible in order to tell the full story of that data's lifecycle? And the way that we talk about that lifecycle is through our auditing plugin, or the ability for iRODS to effectively write down every operation within the system into any number of other ingest technologies, such as the Elastic Stack. We'll speak about indexing. So how does iRODS integrate horizontally with other indexing services? How we can provide the provenance of that data as driven by the audit trail, and how can that provenance drive compliance? Data integrity, as we've discussed earlier, we can talk about how that data is safe at rest on disk. And then publication, we can talk about how iRODS will give you the ability to automatically publish and enforce the published status of that data. Starting with automated ingest, this capability takes 2 particular flavors, the first of which is a landing zone. Now, the landing zone has one specific differentiator from the second flavor, and that is that the authoritative copy of the data is at rest under storage managed by iRODS. A landing zone is effectively a network shared folder. It could be NFS, could be CIFS, whichever technology works for you, that happens to be coincident or co-resident on an iRODS server. This iRODS server will be running the automated ingest framework, and that automated ingest framework will keep track of one or more of these landing zone folders, which are responsible for ingesting data from an instrument or from some other source. That could be gene sequencer, satellites, microscopes, telescopes. Anything that can write something down into a network shared folder has the ability to have data automatically ingested by this framework. Once that data is discovered, then the client-side data management policy is invoked. So this is where we can automatically extract metadata, which is a popular use case. We can provide data transformation, data subsetting, and so on, and then move that data using the iRODS protocol into one or more storage systems that are responsible for accepting the ingest of this data. Then that data is going to be safe at rest within the unified namespace on a server and storage that is managed by iRODS. And then the copy that is going to be in the folder on the ingest server will just simply be moved out of the way, either because it was successfully ingested or because there was an error, and then we will have to try again later. How you manage the data within these folders is certainly a question that you have to answer for yourselves. Now, using the same framework, we have the other implementation wherein we're effectively scanning file systems, and that file system is that single point of truth. That file system is live data that is currently active and being used by scientists or other users who do not wish to necessarily interact directly with the iRODS protocol or one of our presentations, such as NFS, specifically or usually because the scientists tend to enjoy a parallel file system speeds without having the additional protocols in the way. In this use case, we scan this file system and then keep an in-memory cache in order to prevent the catalog from undue pressure. When we discover changes within this file system, then we will reflect those changes within the catalog. And this is where that data effectively crosses the policy boundary. When updates to the catalogs are performed, that is when that data management policy might be invoked. We can extract that metadata, we can compute checksums, we can maintain that audit trail for live data on a live server or a live file system that is not necessarily directly under management by iRODS. So this is very much a popular use case that could in the HPC deployments as well as just for active scientists. Now, once that data is ingested, the question is what happens to that data? What are the additional policies that might be invoked? Data movement is another very popular use case for iRODS, specifically because it can be automated in any number of ways. Given the fact that iRODS has a catalog, we can ask much more complex queries about that data than just the system metadata that might be stored in a file system. So in this use case, the policy effectively relies on metadata associated with these storage resources. Every storage resource has a tag that states that it's participating in a particular tier group. That particular tier group will have a name, and that storage server or that storage resource within the system will have an index. So the iRODS storage tiering group with a name example group and index 0 might be your fast tier. And then an example group with an index of 1 might be your mid tier. So you might have a flash array and then some cheap and deep on-prem object. And then tier 2 might be an archival system using tape. Given that this is metadata, this only means something to the policy that is reacting to that metadata or to the users that have placed that metadata. These indices really mean nothing as far as the policy is concerned. They simply are organized in a particular order, and that order means something to the users who have applied this metadata. Now, the default tiering policy for this use case is, of course, based on access time. So that is, once again, a metadata tag that can be associated with this storage resource. So in this use case, or this instance here, this is 1800 seconds for tier 0, 9,000 seconds for tier 1, and tier 2 has no access storage tiering time because it is the terminal tier. Also, given the fact that this is metadata, it is an atomic operation to remove this metadata tag and then associate it with another storage resource. So, for instance, if tier 1 happens to fill up, we can mark it read-only and simply move this tag to a new storage system that you have just deployed. And then tier 1 can sit there in read-only mode until you have drained it, and then it can be decommissioned or moved on to another particular project or use case. Also, given that this is metadata, you can have as many of these storage tiers as tiering groups within the system as you like, and they can be mixed and matched. So coupling this storage tiering with automated ingest makes a lot of sense, specifically if you have many instruments scattered all over a campus, and each one of those instruments will have a tier 1 close to that instrument in order to very quickly get that data ingested. And then you can automate many tier 0s to a single tier 1, which could participate in many tier groups, given the fact that it can have many of these metadata tags associated with it. And then you may have one common archival tier as well. So this is a very flexible set of policy that can automate your data movement in any number of interesting ways. And if you need to change it, all you have to do is simply move a metadata tag. Now, as I said earlier, we can use the catalog to discover data objects that need to be moved, or as we say, violating data objects. And this is all driven through queries. There's a very simple query to discover data objects that happen to be older than a certain tiering time. But given the fact that we have all of this rich metadata associated with these data objects, we can ask very complex queries. You can find all of the data objects that don't participate in a particular project that happen to have this metadata, additional metadata associated with it, and then those are your violating data objects. Now, given that those queries can be tagged to this particular storage resource, you can have any number of those as well. And every one of those queries will be executed in order to discover those violating data objects. So you can build very complex use cases simply by associating metadata with these storage resources, given that this policy is configured. Now, moving on to indexing, one of our other capabilities, this once again is also driven by metadata. As I said, data-centric and metadata-driven. We can associate a metadata tag with a collection of data to indicate that this collection of data should be taken and sent out asynchronously for indexing. So if we look at this collection here, it is tagged to be participating in an indexing policy. This is going to be given a specific indexing name, and it's going to be given a specific index type. That name could be anything that is configured in your particular indexing technology, and then in that indexing type would be full text or metadata. We're either going to index all of the data in that data object, or simply the metadata associated with that data object for very performant discovery. And as I said, this could be a particular technology. Now, this policy framework, its sole purpose is to react to these metadata tags and then simply schedule these indexing jobs asynchronously. iRODS doesn't necessarily need to know much about the indexing technology or how that data is being indexed, because that is a separate policy implementation, and it is the responsibility of that policy in order to deal with that technology based on the indexing name and type. And in a very similar capability, publication reacts in the exact same way. We can publish a particular collection of data, or we can publish a particular data object, and that is simply driven by these tags as well. This tag indicates that this collection of data is going to be published. It is going to be published to a particular service, and that policy implementation for that service will take care of bundling up all of the metadata, checksums, and whatnot that is necessary for that publication. It will issue a persistent identifier based on that policy as well, associate that identifier with all of the data within this collection, and then this collection will become immutable. Now, you can remove this as an administrator, in which case that data will become mutable again, and then the user will be able to interact with it in a particular right if necessary, but it's not responsible for unpublishing the data with the service itself. So this is how we get data from that automated ingest all the way out to institutional repositories through publication. Now, at the top of the stack, so we started at the bottom with the iRODS technology with the 4 core competencies. We discussed what policies are and how they can be fit together in order to the capabilities at the 3rd tier. And at the top of the tier is what we call deployment patterns. As a consortium that spends a lot of time interacting with the community and understand how they interact with and use this particular technology, we've seen a number of different patterns emerge from the community as to how they have deployed this, whether it be within an HPC context or for publication for grid computing or on-premises analytics and whatnot. We have discovered these various patterns and then from there built out these stories around them in order to help new users within the community bring their deployments up to speed. The first of which that we have here is file system synchronization. So if you look on the left here, we have our file system scanner. This file system is the single point of truth. This is live data that is interacting with the scientists or vice versa. And then from there, the question is what happens to that data once these changes cross these policy boundaries? In this particular use case, our users very much want to synchronize data that happens to be on-prem into another storage technology, which might happen to be off-prem and is very often in the cloud or in a multi-cloud deployment. So as these discoveries are changed, the policy within the system itself is responsible for synchronizing the replicas that are the authoritative replica on this file system into one or more storage systems on-prem or off-prem or in one or more cloud systems. Now, this gives our users the ability to, in the future, have a cloud-native approach. If for some reason they want to decommission this particular storage system, they can simply mark it read-only, perform one more synchronization, and then simply decommission it, at which point all of their data is safe in the cloud or in a multi-cloud deployment and still available through the iRODS protocol within that unified namespace. So this is merely a coupling of the file system scanning capability with additional policy in this deployment pattern. Now, one of the first pattern that we have discovered out there is how iRODS is deployed within a HPC context. So how does a data management system interact with very fast scratch file systems and thousands of nodes? Once again, on the left, we have the automated ingest capability. In this instance, we're discussing it as a landing zone. That data is discovered, it is moved to long-term storage, metadata is extracted and applied for discoverability, and it will sit on long-term storage until the users decide to take that data out to compute. Now, in this use case, it is managed within the iRODS unified namespace, and that data is replicated out to Scratch file system under iRODS management. So this is a second replica of the data at rest on the Scratch file system. And then from there, that data the job can be launched either by the user, it could be by iRODS or a bit of both. Regardless, iRODS stays out of the data path for the compute. This is why the orange HPC box is sitting outside of the namespace partially, because those job runs at parallel file system speeds. And the interesting part to us for the data management purposes is simply what are the results of that compute? We know where the data was ingested from the landing zone. We know where it has been at rest. We know that it's been replicated to Scratch. If iRODS is part of the actual job itself, we know what has happened to that data. And so the question here is how do we gather those results, either through a landing zone, file system scanning, or some other method. We can then replicate that data back to long-term storage and then trim Scratch. So iRODS can be responsible for grooming Scratch for future users in order to maintain a low utilization. And then we have now a virtuous cycle of provenance from the origins of the data to the results of the analytics of that data as many times as your users happen to want to run those jobs. Now, this is very much an on-premises solution, and we can take a look at an on-prem, off-premises solution where we have data that has been routed to where it must remain at rest. So in this use case, we want to take the compute to the data, not the data to the compute, because we routed that data to where the GPUs were already configured with that storage, because this blue box has some compliance around it like HIPAA or GDPR, and we are not allowed to remove that data from that storage, or because it's in the cloud and we do not want to pull the data out of the cloud, which may be very expensive because it is very large, in order to run the analytics. So in this use case, through that policy layer, as I said, with that horizontal integration across all of that infrastructure, we can containerize your analytics and run that where the data is at rest and simply capture the results, much like we discussed with the HPC use case. So if you have large genome sequences here and you simply only want to interact with short sequences within those BAM or CRAM files, you can simply containerize that application, run it there, and then just capture those results. Now, those results may need to reside on that blue box, or they may not. You may be able to move them to some storage that has fewer restrictions around it, or those results may just end up right back into the cloud. Now, this is very much an on-premises and off-premises solution because we can containerize and run locally within our own clusters. Or as I said earlier, speaking to federation, we can actually run this container across institutional boundaries where the data of interest is at rest in our collaborators' infrastructure. And a new pattern that has emerged is the data transfer node. So the question that is answered here is how can we publish data from the edge for other users in order to collaborate either within an HPC context or another without having to have users in the loop? What we are preventing here is a user rsyncing data to a Science DMZ or a Fiona node where it may become accessible via a REST interface or some other protocol, and then just simply leaving it there. So we want to provide the full story around this data, including when this data is replicated for publication across one of these services. In this use case, we have your standard long-term storage, we have Scratch, archival, what have you here within the unified namespace. And then at the edge, we have replication policies configured that will synchronously replicate the data from where the data is at rest in order to make it publicly available over these protocols. And when that data ages out through our cache management policy, we'll simply trim it at the edge for security purposes. First of all, this keeps the edge servers under as low utilization as possible, and also provides additional security because we don't have data sitting at the edge unnecessarily when it's not being used by your collaborators. All of this is very much a composition of a handful of policies for cache management and replication, and then the configuration of your data movement protocols at the edge, which may be a off-the-shelf REST or S3 protocol, or the iRODS protocol itself, NFS, or so on. Now, ultimately, we talk about iRODS from a data management model, and we went from the bottom up here. We started with the core competencies, we addressed policy, we addressed these capabilities, which you see on the screen here. We talked about these deployment patterns, and all of that comes together in the iRODS data management model. How are we going to pick and choose these particular iRODS capabilities for deployment or even for proof of concept? And then what are the patterns that we want to follow for the deployment of these capabilities? Do we need to concern ourselves with users in an HPC context? Do we need to concern ourselves with getting our users' data off of aging file systems and synchronized out to the cloud in order to move to a cloud-native strategy? And do we need to do a bit of both of those? Or do we need to deal with the ability to containerize our applications and work within these various workflows? So this is where we can put this sheet in front of our users, allow them to draw a line around all of the things that look interesting, and then discuss what the necessary configuration is for a particular deployment. Now, having discussed the technology itself, we can move on to some use cases of actual consortium members and what they have in production today. The first of which is the Wellcome Sanger Institute. Sanger has been running iRODS for nearly a decade at this point. And if you blur your eyes a little bit, you'll see that this effectively looks like the data to compute pattern. We have any number of instruments over here providing sequences, which are dumped into staging storage, which we happen to call a landing zone, wherein they provide or perform QC and alignment and then move that data to their Scratch file system for analytics. This data may reside there for any amount of time until they are done with the analytics, at which point they move that to long-term storage and then publish that data to their website. Now, Sanger uses a number of features within iRODS quite heavily, the first of which is replication. They write data preferentially to the green room, and then they replicate that data to the red room, wherein they perform checksums in order to make sure that data is safe at rest before their users can interact with that data in a read-only fashion. What is not pictured here is a third data center where they provide asynchronous replication to a remote server for durability purposes and disaster recovery. Both the green room and the red room are used for read-only access and not the third replica of the data. Sanger is also a heavy user of metadata. They have any number of dozens of metadata attributes that are associated with a data object, and this metadata is used to drive their analytics. When they're generating cohorts of data to take that out to compute, this is all driven by metadata, not necessarily metadata that is associated with a collection name or a particular file name, but metadata within the catalog that is driven by query at the command line. And one of the innovations that Sanger has provided is their use of federation. So federation initially was considered as something that can cross institutional boundaries, and what Sanger has done is created a single iRODS zone for authentication, and then from there, those users may or may not exist in any one of the actual project zones. They have isolated each project into their own zones on their own servers in order to provide the ability to have very strong assertions across the project boundaries and who is and is not allowed to actually interact with that data. So our scientist Alice from earlier may exist within the sequencing zone and may also exist within the human genomic zone, but she may not exist within UK 10K or the archive zones. Given that fact, it is impossible for her to interact with any data with any of the zones in which she does not exist. As you cross these zone boundaries, each one of these systems can also have very strong assertions about what data management policy is invoked, because if you are interacting with the server across one of these zones, that zone's data management policy is in effect, not necessarily the policy where you have authenticated originally. Now, we have seen this pattern be deployed by any number of consortium members and users throughout the community, and this has become a very popular way to organize large companies or large organizations, such as our enterprise users like Bayer. Some of our other users, Maastricht, oh, excuse me. That is a feature that I have not grown accustomed to at this point. And here we go. So within Maastricht, they have used iRODS in an innovative way in order to fuse electronic health records, as well as various semantic and ontology technology with data at rest within the iRODS system, and provided a semantic search capability outward facing to their users. So we have the combination of electronic health records as metadata associated to data object at rest within iRODS, and then those are provided out over their own API for their own web front end, as well as over WebDAV and a number of additional technologies. And they are surfacing data both within on-premises within the hospital, as well as on-premises within their university. So if we drill down into this a little bit, they have data at rest within the university, they have data at rest within the hospital, all provided through the iRODS unified namespace. They have archival data at rest within SURF, which we'll discuss in a second. And all of this is fused with electronic health records for discoverability purposes. So they have their own web portal, which surfaces the Discover semantic search technology, as well as folders on the user's desktop over WebDAV. They've presented a REST interface, Python interface, and various other web interfaces to all of this technology that is being virtualized through iRODS. Now, speaking of SURF, SURF is providing iRODS as a service on premises within their virtual hosting environment, wherein they give you the ability to provide your own server instance of iRODS that can participate in your namespace. And what this does is gives them the ability to provide their existing infrastructure through that service layer to your unified namespace and your iRODS deployment within their data centers. So they are providing object storage, archival storage systems, as well as disk storage for users through their virtual hosting environment to any number of universities throughout the Netherlands. And the Astron Radio Telescope project is also using iRODS in order to archive data within SURF as well. So this is very much, excuse me again. So this is very much them using servers to participate in their unified namespace. And then on the other side of that is the EUDEP project, where they are providing data across institutional boundaries using that federation capability. So we have zones within each university, which I believe are about 27 different universities. And then from there, they're federating these namespaces together and then providing that data access through the iRODS protocol, as well as the ability to provide data movement via grid FTP for HPC purposes. So if you happen to be at Maastricht or Groningen, or any one of the other participating universities across the 27 different instances, you have the ability to create these virtual collections of data across institutional boundaries, move that data to your HPC system, and then from there, provide or generate your analytics, and then provide those results back out to the community. And that is the end of my presentation. Are there any questions?
Well, thanks very much, Jason, for the overview of iRODS. If anyone would like to ask Jason a question, please write it now into the question box. And just while we're waiting for any questions to come through, Jason, I wonder if you could tell us about your activities in Australia. Agriculture Victoria is a member of the iRODS Consortium. So can you tell us anything about that relationship?
Absolutely. They've been a member of the consortium for a couple of years now. We originally engaged with them in order to manage the Internet of Things. So they have a number of smart farm projects. All through, I believe there are 5 research farms, as well as a number of other participating farms, where they have various devices that are attached to various things, anything from a plant to a cow. And they are gathering all of this data at the farm. And the issue that they have there is that there's very little internet access out where these farms happen to be. And from there, they wanted to answer the question of how can you maintain and manage that data in a generic way and get that to their HPC center BASC, where they can run their analytics on that data, and then provide that provenance as well. So we're providing that abstraction layer between the Internet of Things platforms and their underlying storage locally, and then from there, the ability to get the data out to analytics. We have also engaged with them on a second project right now where they have drones that are flying over crops and bringing in terabytes of data of reflectance imagery in order to provide analytics on how the crops are performing. And that is a very similar strategy where we are gathering all of that data, pulling the metadata out, making that data discoverable, and then being able to bundle that up and then ship it off to compute. So this is very much a automated ingest and then a data to compute deployment on premises. And we are going to be interacting with them as well on a couple other deployments coming up, I believe, actually involving some wet labs.
Fantastic. We have a question that relates to that international deployment. Which centres and places are considered best practice internationally as far as their deployments go? Can you talk a bit more about those?
Can you repeat the question again? I don't think I quite understood.
Which centres or places are considered best practice internationally as far as their deployments?
The University of Utrecht is probably one of the most active members of the community, and they have very much spearheaded the standardization of iRODS throughout the Netherlands. At this point, I believe that there have been successful deployments at all 12 universities, as well as SURF, which acts centrally there. And they have done a fantastic job of providing us feedback as far as what needs work and what could be done better, and have really much provided an exemplary example to the community. As I said, Sanger has been running this for 10 years, and they are also a fantastic example of how to use iRODS as well. And if there are, and the last one that I would point out is the National Institute of Environmental Health Sciences here within the United States. Those are the three top deployments and users of iRODS that I would generally bring to the table to introduce to a new user.
Great. And can you give examples of the sort of expertise and effort that's required to locally manage iRODS?
Okay, your standard system administrators are a great place to start. Sanger has, I believe, 1.5 FTEs to manage all of their deployments on site. And we're talking a significant number of users and a significant number of servers. At the University of Utrecht, I believe they also have 1 to maybe 2 people to manage all of the data across all of their projects. So it is very much deploying a system like Apache or Postgres or what have you from the server side of things. Now, the interesting part comes together when people need to sit around the table and then make decisions about that data management policy itself, which is very much a different skill set. They may reside in the same people, much like Ton at the University of Utrecht, but that might be a different group of people entirely. But once you build those requirements, they can be delivered back to the system administrators or the data grid administrators, as we like to call them, for implementation.
Okay, we've got a cheeky but useful question here. How can it all go wrong? What are the pitfalls to look out for when deploying iRODS across multiple organizations?
Well, we could address that from a number of different directions. From a technology point of view, it is infrastructure and it can fail, and arguably it will fail. So having your disaster recovery plans is very important. You know, as best practices, you want to snapshot your catalog, which basically is your unified namespace, and keep that somewhere safe. As we saw, Sanger maintains 3 replicas, 2 for durability on site for read, and then 1 for disaster recovery offsite. That is always very important. And then from the other direction, you have the question of how do you wrap something like iRODS around your infrastructure and keep your users from getting angry at you? And this has been one of the more challenging aspects, is the social aspect of the technology, where we have to discuss how things might be done differently in the future in order to provide all of these other, great capabilities that come along with using a system like this.
Okay, and what does the user, for example, the researcher, experience look like when interacting with iRODS? That is, in addition to the APIs, does iRODS have a GUI that users interact with, and what does that look like?
Absolutely. So if we move to my second slide, there is a command line interface that we call the iCommands. We present iRODS over the WebDAV protocol, which is effectively just a folder you can mount on your laptop. And then from there, you can just drag and drop data into and out of iRODS through this particular presentation. Not represented is the NFS presentation. So you could just mount an iRODS collection for a user as a mount point in a standard Linux desktop. Getting to more complicated aspects, we have a web interface called MetaLinks, which was contributed by EMC, and that is very much a rich web experience. It acts very much like the Dropbox view of iRODS, if you will, with the added capability of discovering data through a search capacity. So you can use all of those metadata triples within the catalog through this interface in order to discover your data sets and save those searches out. Very shortly, it would also interact with our indexing capability. And so if you have deployed iRODS to use that indexing, say Elasticsearch, you'll be able to search directly into all of the data itself. And then Cyverse, a deployment from the University of Arizona, has what they call the discovery environment, which is a very, very rich web environment wherein you can actually send apps to where the data is at rest to run those analytics and configure those all through the environment. And there is actually going to be a deployment of Cyverse at the University of Melbourne here in the future.
Fantastic. Well, I think that's all we have time for today. So I'll once again express our appreciation to you, Jason, for sharing your work with us today. Thank you.
All right, very much. Thank you.
To wrap up, I'd like to give thanks to our host, the ARDC, and to acknowledge our funding. The Australian Biocommons is enabled by NCRIS via Bioplatforms Australia support. So thanks to Jason. Thanks very much for watching us today. And until next time, goodbye.